This is 1963 IMO problem number 3, and here is a view of this problem. In an n-gon, A1, A2, An are the vertices, all of whose interior angles are equal, so that's crucial. So this is an equiangular polygon, right? Polygon, or in that case n-gon. The lengths of the consecutive sides satisfy the following inequalities. If that's the case, then we need to prove that in fact all of them must be equal to each other. Okay, let's just make an example. So consider the following example. So what I have in mind is the following. I will be providing two different proofs. Well, at least the first proof will be more like a sketch. And the second one will be using complex numbers, and it will be very similar to the 1990 IMO number 6. If you can watch my other video, 1990 IMO number 6, how I at the beginning of that video I give a 10-minute or 8-9 minute explanation of how to handle polygons using complex numbers. Awesome. So let's first start with the sketch. Let's go ahead and consider the case where n is, say, equal to 6. We have a hexagon, and let's see if we can do it. Let's just consider the first edge, A1. It's the largest edge of our hexagon. I don't know how to draw a hexagon, to be honest. I hope I can draw something reasonable. Okay. Well, not bad, I hope. Well, except this one. Okay, so I have my hexagon, and pretend this is a regular hexagon. All the angles are equal to each other. So consider the following. Let this be let's call this point P1, and that's the first edge. So this is A1. Then A2 will be less than or equal to A1, but it will have the same angle. So as you keep drawing it, so it will look like something like this, right? That would be edge A2. And then we will make A3 will be lower. So if it's strict, I want to see if that's even possible if we have strict inequalities, right? So that would be an A3. By the way, this one was vertex P2. Sorry, not P2, A2. Sorry for that. So the vertices are A's. A1, A2, A3, and the same story, right? And then we need to make a turn. And by the way, how do we make the turn? It's very easy to imagine it simply by taking a slice out of it. So you just draw a parallel line. We'll do the same thing here. So you can just draw this parallel line to this side, right? And so therefore it's easy to make the turn, and obviously because of corresponding angles, these angles will be the same. Because of corresponding angles, obviously these are also 120 each, and so on. Alright, so we keep going, but we need to make sure that A2 has a length less than or equal to A3, right? So after a while, so we just stop there, and then we do the same trick. All I do is I draw a line parallel. So this line is basically parallel to this one, right? So let me put the parallel sign, the decorations on this side. Yeah, so those two lines are parallel, and then this one was A4, and then I draw A5. A5 is potentially less than or equal to, and finally I'll draw a parallel line, because something which is parallel to this. And wait a second, do you guys see what I see? There's no way that this vertex here, so this one is A4, this one is A5, and this one is A6. There's no way that this one would be A1, right? So these two were supposed to be connected. So they are supposed to be connected because it was supposed to be a closed polygon, right? But obviously they are not connecting. So how to express this in how to write a proof out of this, right? So obviously that's why I told you I want to just give a sketch, but just to give you an idea, one way you can handle it is the following. This largest hexagon, where the side length is A1, as you can see, so all the sides are A1, so I can call this hexagon as, say, H1. And the second hexagon, whose side length A2, does everyone agree that because the side length is on the sides of H1, it has to be something like this? So A2 is probably like this. It's a hexagon which is totally contained in H1, right? So H2 is totally contained in H1, and then you keep drawing H3 here, obviously, right? So H3 is slightly smaller than H2. So H3 will be like this. So H3 will also right, so because H3 is less than A3, yeah, H3 has side lengths less than A2, it will not quite hit here, so it will be more like this. Does that make sense? So that's H3, and so on. So each of them, so H1 contains H2, containing H3, and so on. So we have this sequence of hexagons. Does that make sense? And at the innermost we will have H6, right? So we have H4 will be this one. So let's yeah, H4 will be slightly more than H3, so it will be like well, smaller than something like this. We'll draw a parallel line here, and then this one, oops, so that would be H4, so that one is H4, and then H5 will be like this. Oh boy, so it's hard to even draw these. So this one is H5, and finally this one is H6. But why did I do all these things? Because obviously H6, so this is H6, the last one is H6. H6 is strictly contained inside H1, right? Unless all the sides A1, A2, AN, and they are equal to each other, like the thing. Otherwise, if it is strict, if any of these transitions is strict, then there is no way that this hexagon, the vertex, will share the vertex with the first hexagon, right? So this is kind of my sketch for a first solution. So think of it as a sketch of a geometric solution, right? A geometric argument. Obviously, you need to explain every step in with a lot of care, because there's a lot of words mentioned here. So that's why I kind of, instead of using this, I want to apply a much more in a sense rigorous way to prove it. So that's why I would like to provide the details of a second solution, a second proof, right? So solution 2, and like I did in like I mentioned earlier, you can check my video 1990 IMO problem, I believe number 6 video. That question is, by the way, significantly harder than this one, obviously. But I explain how to handle how to handle polygons, equiangular polygons, in that video. But just to remind you, it turns out that if you have an equiangular polygon, let's continue, for instance, well, yeah, so why not? So let's consider yeah, let's consider our hexagon again, like that. It turns out that if you have well, obviously this is a regular hexagon, and I probably don't want a regular hexagon. That's why I will do the following. I will go ahead and for instance, if you take a regular hexagon, and let's say that the largest side of the polygon that I'm interested in is this one, then the next one would be, I will do like I did previously. I will just take out a piece from that side, maybe take out another piece here, take out another piece here, and then take out probably that. Oh, okay, so therefore I have this one, then I have this, I have that, and yeah, that's it. I can just leave it like this, and then I have this. Do you guys see that? So I have this weird shaped hexagon, but the important thing is the following. So this hexagon can be expressed in terms of vectors. So we have vector A1, A2, A3, A4, and that's A4, A5 is here, and A6 is here. So in order to have this closed loop for our hexagon, so we started, for instance, at this vertex A and we want to come back to this, it must be the case that it is trivial from vector addition, right, that the sum of these 6 vectors be equal to 0, right, the 0 vector. But indeed, there's an easy way to carry these vectors into the language, or into the complex plane, and think of the complex coordinates, right? And that's exactly what I'm going to do. And it's very easy to do it in the complex plane, obviously, because the angles are equiangular. For instance, in the case of a hexagon, I will be using the 6 roots of unity, and in the case of another polygon, an n-gon, I will be using the nth roots of unity, obviously. Obviously, complex numbers are easy to use to rotate stuff, right? In fact, let me go ahead and I just realized that this numbering is not very nice. So let's have a1 the beginning vertex, right? So I mean the beginning vector. So it will be easy for me. So hold on a second. Let me just change this. So this is a4, a5. A6. So therefore, let's begin. So in the complex plane, so let's think of this as the real axis. Let's just change color because this is not good. So think of it like this. So you have this complex plane like that. We want to add these vectors, right? So let's start with vector a1. A1 is just horizontal. So therefore, a1 is just a1 plus a2. Well, a2, don't worry about a2, not because you know vectors can be shifted. So this vector can easily be shifted to the center, right? So to the origin, right? So therefore, this is our vector a2. How do I express that? Obviously, this is the external angle. External angles matter. So I forgot to say that. So the sum of the external angles of any polygon is obviously 2 pi, and because our polygon has n sides, 2 pi over n, or in this particular example, it is 2 pi over 6, obviously, right? So this angle is 2 pi over 6, meaning this angle is 2 pi over 6. So this one was a1. So therefore, a2 is simply all I do is I measure the length, obviously it's a2, and I multiply it by CIS 2 pi over n, right? So CIS 2 pi over n. That's it. And I keep doing that. So I will probably need more space. So A3 would be simply A3 times CIS. Well, for A3, notice that so A3 will be shifted here, somewhere here, I guess. A3. We will do 2 pi over n twice, right? So it will be 2 times 2 pi over n, or if you will, 4 pi over n, and so on, all the way up to this is the case for a hexagon, but I can easily generalize it, right? So why don't we just write the general formula? So let's write this an. So it will be a sub n times CIS what am I saying? So we need to do it. So we are rotating it once here. So this one will be rotated n minus 1 times. So 2 pi over n times n minus 1, right? So, or if you will, 2 times n minus 1 pi over n. Does that make sense? And this sum better be equal to 0. Does that make sense? So this is how you can describe a closed polygon, right? And this is exactly what I will be working on. Obviously, in terms of the notation, you can come up with the following shorthand notation. CIS 2 pi over n is simply the nth root of unity. And let's assume without loss of generality that that nth root of unity is epsilon, nth root of unity. So therefore, an alternative way to write this is epsilon square. Remember from de Moivre's theorem, right? We know exactly how to express these. So therefore, this is equivalent to a1 plus a2 epsilon plus a3 epsilon square, and so on, all the way to a sub n epsilon to the power n minus 1 equal to 0. Okay, so now what? What I will do is I don't want to actually use this, but I rather prefer to use this notation. Indeed, I want to further split each one of them. I want to see the cosine and the sine separately, and I want to set the real part of the left-hand side of this huge expression equal to 0, and the imaginary part also equal to 0. Does that make sense? So therefore, let me go ahead and write the imaginary part of this expression and set it equal to 0, and the real part set it equal to 0. Let's start with the imaginary part. So obviously this has only a real part, no imaginary part. We will start with a2, right? Then, right? So the imaginary part of the left-hand side better be equal to 0, right? Because the left-hand side is a complex number, but because the right-hand side is 0, both the real and the imaginary part of that should be 0. Okay, so therefore, okay, let's begin. So a1 doesn't have any imaginary part, so a2, I have a2 times, so cis 2 pi over n, this is just cosine 2 pi over n times I sine 2 pi over n, so therefore, yeah, therefore the imaginary part would be just sine and sorry, sine 2 pi over n, sorry for that, sine 2 pi over n, plus the same thing with a3, right? a3 times sine 3 pi, sorry, 4 pi, sorry for that, 4 pi over n, and I will go all the way up to the last term, which was an sine, I believe I called it 2 pi over n times n minus 1, right? So therefore it is 2 times n minus 1 pi over n, and that better be equal to 0, like I said earlier. So you can see here that we have in total, so we started from term a2 all the way to an. So in this expression we have n minus 1 terms, and what I do is the following. I just would like to pair these terms. Indeed, I will pair this term with this one, and I will do every single term like that. So I will pair the kth term with the n minus kth term, and so on. So does that make sense? So the second term, let me see. Right. So this is my first term. I'm pairing it with the last term, right? The nth term. Sorry. Hold on. Yeah, oh sorry, it has n minus 1 term, sorry. So therefore this is my first term, I'm pairing it with the n minus first term. I'm gonna pair the second term with the n minus, well obviously it's somewhere here, n minus second term, and so on. So therefore pair k term with n minus kth term. Well, I can do that. Obviously, if I have an even number of terms, meaning if n is odd, there is no problem. All of them are paired. But if I have an odd number of terms, then I will have a middle term. So let's have a look at both cases separately. So let's assume that n is odd, meaning, so this implies that we have n minus 1 is even. So and all terms are paired, like this one. So what is a typical one? So for instance, the kth term would be well, the sign of the kth term would be sine k times 2 pi over n, and I'm gonna pair this with sine of, remember that I'm gonna pair it with n minus k term, right? The one goes with n minus 1, and so on. So therefore it will be paired with n minus k term, like that, 2 pi over n. Now let's have a look at this expression here. So this is just sine of, well, I can just expand it, right? So n times 2 pi over n, which is just 2 pi. So I'm just distributing this. So this is just sine of 2 pi minus k pi minus 2k pi over n. Does that make sense? But then this is just, hey, sine 2 pi over minus, this is just minus sine, right? So this is just minus, or sine minus 2k pi over n, which is just minus sine 2k pi over n. Look at this. These are the same things, except that it comes with a minus sign. So therefore, when I reorganize these, rearrange this expression here, so I'm going to rewrite this by pairing these terms, right? So I have this term paired up with this, it will look like this. It will look like A2. So therefore, let's call it star. So therefore, star is equivalent to, so star is equivalent to what? So I have A2 minus A sub n, and they both have this, well, okay, let me do it in 2 steps. So this is just A2 sine 2 pi over n minus an sine does that make sense? So we will have this guy, but k is 1 in this case, 2 pi over n, right? Hey, the sine 2 pi over n are common, so I can factor it out. So finally, so that's why I was planning to write it as A2. So let's cut it short. It's just A2 minus an sine, sine what? 2 pi over n. And we continue like this. Then we will have A3 minus an minus 1 sine 2 pi, 2 times 2 pi over n. Right, so which is 4 pi over n, and so on, until the middle terms, which is like complicated looking. And to be honest, I don't. Yeah, okay, let's just do it. Let's not be lazy. So what is the middle guy? Yeah, I mean, I think I calculated right. I think that the terms would be n plus 1 over 2, and the other one would be n plus 3 over 2. Can you guys check it? And you can post it in the comment section, obviously. Sine of, obviously we do 1 less, so 2 pi over n times 1 less than this, so which is n minus, okay, so this is really ugly looking. And hopefully it will, I mean, yeah, it won't be crucial. You will see in a minute that they will all cancel out anyways. Okay, so this is equal to 0, right? Now let's have a look at this expression. So we want to make so we need to make this equal to 0, and look at all these signs. Because we did a pairing business, you just realize that all these angles, obviously this angle is less than 180 degrees, less than 180. When you start from the beginning, half of them will be less than 180 and the other half will be greater than 180. But when I do the pairing, I just take the little one, right? Because I decided to rewrite the big one as minus the little angle, right? So therefore what will happen is all these angles here, here, and here too as well, they are all, and look at this, so the 2's cancel out, n minus 1 over n times pi. Obviously even this one is less than 180, right? So all these angles are less than 180. So therefore the sine of all these angles are greater than or equal to 0. So these terms are all greater than or equal to 0. And we want to add all these terms. Look at these now. A2 minus an. Remember the condition given at the beginning of the problem. A1 is the largest, A2, and so on. So an is the smallest, right? So therefore, look at this. This is obviously less than or equal to 0. The same thing here. Less than or equal to 0. Less than or equal to 0. Wow. So therefore, the only possible explanation for all these terms to add up to 0 is, so notice this, so when you multiply them, this is less than or equal to 0, less than or equal to 0, so you have so many terms, n minus 1 over 2 terms, all less than or equal to, well, n minus 1 over 2 terms, right? And all of them are less than or equal to 0. The only way they would add up to 0 is if every single one of them is equal to 0. Obviously, well, oh, sorry for that. So the sign of each one is strictly greater than 0, my bad. So the sign here are all strictly greater than 0. Sorry for that, because these angles obviously can't be 0, so then we won't have a degenerate, non-degenerate polygon, right? Okay, so therefore the only explanation for this is they have to be 0. Each one of these has got to be 0. Actually, I can just focus my attention on the very first one, right? So we know that so therefore a2 minus an has got to be 0, but this implies that a2 has got to be equal to an, right? But remember the given condition early on. So early on the problem said that a2 is greater than or equal to an, right? So we had this sequence, but we know we know that a2 is greater or equal to a3, which is greater and so on all the way to an. How do you reconcile this with that? The only explanation is that, so therefore this implies that not only a2 is equal to an, but everything between them, by the sandwich theorem, all of them are equal, right? So a2 is equal to a3, blah, 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 all the way to an. They are all equal to each other. But then you might say, hey, this is just the odd case, right? Remember early on I said when n is odd. If n is even, we will have a term in the middle, which we will not be able to pair. But that middle term will simply be, if you do the calculation, so n is even. So when n is even, then n minus 1. So we have, because in that sum, this sum has this star sum has n minus 1 term. Then this implies n minus 1 is odd, and the middle term is not paired. So this middle term is not paired. But what is that middle term? So the middle term will be a sub n plus 2 over 2 times sine of, obviously because n is even, this is divisible by 2, sine sine pi, right? Because think about it. So you have the unit circle and you have an even number, so therefore this is your well, this is the first root of unity, epsilon, and then you have epsilon square and so on. The middle guy would be right here, right? Does that make sense? So this would be your so therefore it will have an angle of pi. Whew, but sine pi is just 0, so the middle term will be 0 as well. So the paired terms, will be equal to each other, and so therefore it doesn't create any problem. So we can the result still applies, right? So the pairing trick still gives us the desired result. Now finally what? Let's now go back to our original problem, and like I said at the beginning, if we want to have this sum equal to 0, both the imaginary part and the real part must be 0. We have taken the imaginary part. Hold on. I won't even need the real part actually. Let's go back to this expression and let's just replace a2, a3, all of them all the way up to an with say a2, right? Because now they're all equal to each other. They're all equal to say a2, right? So therefore our expression, so let's continue here. I don't need this. So let's just get rid of this. We decided we will be using the we'll be using in full details. Okay, so therefore this expression now has become a1 plus a2, factor out a2 and everything inside. So now I will be careful and I will well, okay, let's just write it, I guess. CIS 2 pi over n plus CIS 4 pi over n, and so on, all the way up to CIS, the last one, 2 n minus 1 pi over n. Oops, that one is a square brackets like this, and we need this thing to be equal to 0. Now, do you guys see the inside? Oh, I should. So we are going back to that notation. So this one is the first root of, the nth root of unity. This is the square of that nth root of unity, and so on. So this is the n minus first power of it. And look at this sum. So, those of you who are already who has already studied this already know that this is just equal to minus 1. Just in case you don't realize it, you can just realize that this epsilon solves. So epsilon solves the following equation, right? So x to the power n equal to 1, right? That's why we call it the nth root of unity. But then, or if you will, you can call it z, doesn't matter, z to the power. But then all these roots are missing one, which is the epsilon to the power n, right? So I'm adding all these except this one, right? So these are the n minus 1 roots of this equation, but this equation has n roots. The last root is this one, which turns out to be just equal to cis n times 2 pi over n, and so this can cancel. So cis 2 pi, which is cosine 2 pi plus I sine 2 pi, and that's just 0, so that's just equal to 1. So we are adding all the roots of this equation, or if you will, let's rewrite it like this. Consider, so we are just adding the roots of this polynomial here. P of z equals z to the power n minus 1. So we are adding all the roots except 1. So what is the sum of the roots here of this polynomial? Well, by Vieta formulas, Vieta, we know that the sum of the roots, because it's missing the z to the power n minus 1 term, the sum of roots, the sum of the roots, which is the epsilon i's, I equals from 1 to n, including the 1 here, including this one, is supposed to be equal to 0. But remember that our sum misses this one, right? So this one. So therefore, all these numbers should really add up to minus 1. Boom. So that gives us the desired result. So therefore, this gives us a1 plus a2 times minus 1 is equal to 0. And finally, we have found even the last guy. The last guy is also equal to a2. So therefore, all of them, all of these coefficients has got to be equal to each other. Otherwise, our polygon will not close, and that solves the problem. Hope you enjoyed the video, and looking forward to see you guys in our next lecture.